Nuclear power is the future of energy and could be part of the solution to solving the climate crisis. There are many different types of nuclear reactors, and in this video I'll only talk about light water reactors and liquid fluoride thorium reactors. Light water reactors are famous in a sense. All three of the large nuclear tragedies occurred at light water reactors. In light water reactors, uranium fuel is used. Through the process of fission, the nuclei of the uranium atoms are split, and when they split, they release loads of thermal energy. This thermal energy is used to heat water into steam that then turns a turbine. In these reactors, there are two main isotopes of uranium, uranium-235 and uranium-238. Uranium-235 is fissile, whereas uranium-238 is fertile. Fissile means that when hit with slow-moving neutrons, or thermal neutrons, the nucleus is likely to split, which is what ends up giving out the energy. Fertile means that instead of splitting the nucleus, the neutron is more likely to be absorbed by the nucleus. When uranium-238 absorbs a neutron, it becomes plutonium-239, which is a bad element. Plutonium-239 is what is called a transuranic actinide. These are the heavy elements at the bottom of the periodic table, and they are very radioactive, can't be used for fuel, and have incredibly long half-lives, like tens of thousands of years long. And this is what ends up as a nuclear waste that we can't safely contain. In order to get a good chain reaction going in a uranium nuclear reactor, uranium first has to go through an enriching process, which increases the amount of uranium-235 to 238. This enriching process can be super expensive, and this is why we see a lot of light water reactors in use today. They require minimal amounts of enrichment and therefore are much cheaper to maintain. Light water reactors, as the name suggests, use water as the main coolant in the reactor, which has basically been causing all the problems. There is much infrastructure in factories to make sure that the coolant water doesn't boil and end up allowing the reactor to overheat. And this requires a lot of active effort. And if there's one slip up, the reactor overheats exponentially, and this is what causes all the nuclear disasters. So how can we make nuclear power safer? Well, let's take a step back and go over to lifter reactors. Lifter reactors use thorium-232 as its fuel. Thorium has 2 less protons than uranium, and thorium is a fertile element. And you might be like, hey, you just said a while ago that being fertile is a bad thing for uranium, and you're right. But for thorium, because it's fertile, once it absorbs a neutron, it goes through the process of becoming uranium-233. Uranium-233 is very fissile and very efficient compared to even uranium-235. Being fertile also means that in the reactor, if something goes wrong and an overheating process begins, the thorium will stop reacting at high temperatures because it requires a helping element to sustain collisions. This allows thorium reactors to have what we call walkaway, or passive safety. So having huge explosive meltdowns are basically impossible for thorium to accomplish. The waste products from uranium-233, while they're still reactive, are not transuranic actinides, and therefore have a half-life of only around 300 years, which when compared to plutonium's half-life is pretty impressive. So thorium could be the future of nuclear power and energy harvesting as a whole, but there's still much more research needed to be done before we can start plopping liquid fluoride thorium reactors everywhere.